This week we are looking at Chapter 4. Specifically, we're looking at coordinate systems, and Chapter 4 starts on page 111 in your textbook. So make sure to open up to that. Go ahead and follow along with the PowerPoint presentation. I also want to caution you, as we're going to be talking about coordinate systems, a huge and very important component to coordinate systems is going to be map projection. So you're going to see that a lot of this is going to come back up. And so I know that it's been a few weeks, basically I think 5 weeks since our week 1 module where I asked you to watch these 2 videos. What is a map, the components that make up a map, and another video specifically detailing why map projections are wrong, or basically the difference in how one projects data and how a map projection is always going to have some form of distortion. So if none of this is ringing a bell, I highly recommend pausing the video right now, jumping back to the Module 1 videos, and maybe watching these again, as I truly believe that this will help set up a stronger foundation of the knowledge base needed so that we can talk about coordinate systems. So I recommend to go ahead and do that now. And once you're done, come back and we'll continue with this presentation. Before we learn about a standard coordinate system, we need to talk about what the backbone of any coordinate system is going to be. And the backbone of any GIS dataset is going to use X and Y values to locate geographic data. Sometimes there's also going to be a Z, and you can see on this graph, X and Y represents horizontal planes, and a Z is going to represent the vertical plane. But for the most part, the choice of values in the coordinate system is going to be predetermined, and the data set is going to be georeferenced, meaning that you're going to be able to lock into a specific area. Ultimately, in order to display and analyze maps on a digital screen, a GIS system will use coordinate pairs, which specify the location and shape of a particular feature. So for our case, the majority of the data sets that we're going to be using are simply going to have X and Y coordinate pairs. And these coordinate pairs are going to allow us to define points, lines, and ultimately polygons. So as I just mentioned, a coordinate pair is a specific XY coordinate. A point is described by a single XY coordinate pair located within space. A line is going to be a culmination of a series of XY coordinates. And a coordinate space is an agreed upon range of coordinates used to portray features. So again, a single coordinate pair is going to produce a point. A collection of coordinate pairs is going to be able to form a line. And you can still use these coordinate pairs in order to create a predefined space in order to create a polygon. And so you'll notice that anytime we're looking at a feature in a GIS that has a polygon, such as a building footprint, that is going to all fall under a predefined coordinate space. It's also important to note that XY coordinate pairs using numbers to define your X and your Y locations are ultimately arbitrary until they are defined. So if you were to plot a point and you weren't referencing to any specific coordinate system, then your location, your XY locations are just going to be floating around somewhere wherever that arbitrary 0 location is going to exist, which would predefine where your X and Y coordinates are located. So in order to avoid that problem, what do we do? More or less, we have to rely on standardized coordinate systems. A standard coordinate system is a coordinate system whose characteristics are defined and established according to cartographic standards and tied to a specific location on Earth's surface. And while it's important to note that there are a plethora of different coordinate systems that can be used to georeference specific data points, for example, this map shows the use of a latitude-longitude system, a UTM, and a state plane system. A UTM meaning a Universal Transverse Mercator map system. It's important to note that there are 3 different points or 3 different reference systems used to reference the location of this Dottie school. But because all of these different coordinate systems are predefined and have predefined locations, it is possible to mesh all of these together, put them on top of one another so that all of the different coordinate systems actually match up. So despite there being a vast number of different coordinate systems, there are 2 main types of coordinate systems. We have a geographic coordinate system and a projected coordinate system. The geographic coordinate systems can be based on spherical coordinates. Again, that is using prime meridian and the equator. If you think back to the initial lab map coordinate points that you had to do in order to find XY coordinates on the map, that is in essence using this spherical component of the Earth to find specific locations. As well as a projected coordinate system, which is again that mathematical component where we are taking the spherical data and projecting that onto a flat 2-dimensional piece of paper. So we talked about the variations in the types of projected maps that there are. So most importantly is to note that these are the 2 main types of coordinate systems that will be used to georeference or locate your coordinate systems. Again, this is what will anchor your X and Y coordinate pairs to a specific location on Earth, where you're going to be able to match up all of your other data with other existing coordinate systems. Every feature class stores its XY values based on a specific coordinate system. For example, in this example, the state's data is projected and the road's data is unprojected. So it is going to, the state's data is going to store its coordinates in meters, while the road's data set is going to store its coordinates in degrees. So again, don't forget that the unprojected is going to be this geographic coordinate system, while a projected data set is going to be the process of taking that 3-dimensional globe onto a 2-dimensional map. Diving a little deeper into the geographic coordinate system, it's important to note that all of the geographic coordinate systems use longitude and latitude values, and generally that is going to be in the form of angles and degrees. So for those of you that don't remember the prime meridian, this is the 0 point when we're looking at longitude, and the equator is the 0 point when we're looking at latitude. And so you can think of both of these axes as the 0 point. And so when you are going north, you are actually going up a certain angle from, in essence, the middle of the globe. So if we're going up from the equator, a 45-degree angle, right? A latitude of 45 degrees, this is a 45-degree angle. That is in essence what is going to make or define the location of this latitude line. And you'll do the same when you're looking at the prime meridian and when you're moving left and right or east or west longitudinally. So from this center location, just as when you moved north and south for latitude, when you're moving east or west longitudinally, you can go 10, 20, 30, 40, 50 degrees to the west, or 10, 20, 30, 40, 50 degrees to the east. So when you're looking at that X and Y coordinate system, or those X and Y points, the point values or the X and Y values are going to be stored in the terms of longitude and latitudinal measurements, specifically looking at angles north, south, east, or west from this 0 point where the prime meridian and the equator meet. So for a quick example, if we're looking back up here on the previous slide, we can see that the roads data is unprojected, meaning that it is just the geographic coordinate system. And you can see how this data is stored in negative and positive values, and that is because we're looking at locations or points that are going to be north or south or east or west of that 0 point. But how do we get even more specific? So when we're looking at or more precision using a geographic coordinate system, that is a CGS, it's important to note that all of these different angles can actually get boiled down. Again, mathematically, we're not really going to go into this, but it is important to note that using degrees, minutes, and seconds is going to allow you to become even more precise in finding a specific geographic location, and is going to allow us to create better accuracy. And in order to achieve this, we actually have to take our latitude and longitudinal numbers, right, those north, south, east, and west numbers, and convert those to decimal degrees to store this location in our GIS. Jumping back up here again, you can see that that is why there are also all of these additional decimal points. This is the conversion from degrees, minutes, seconds back into north, south, east, and west locations. All right, taking a look at the shape of the Earth. If you were not already aware, but our Earth is not perfectly round. So while a sphere is ideally perfectly round, Earth is not a sphere. Its official shape is more of a spheroid, so it's an oblong sphere. And it gets worse than this, and the fact that is, Earth is not perfectly round. So it has edges where it goes up and down because, again, it is really just a giant rock floating around in space. So its most accurate description of what the shape of Earth truly is going to be a geoid, which is this not smooth, not round sphere. So it is still going to be stretched along the equator, and again, that is due to how quickly Earth is spinning, and that is being pulled out left and right. So the equator is the largest circle, great circle around Earth, and from north to south, this distance is less than the distance between this side. And so it's important to note that the geoid is basically the starting point for how we figure out the datum, or where all of our coordinate systems are really going to be georeferenced. So the short version is that a geoid is a surface model from gravity differences and is closest to the true shape, but it is too complicated for mapping. So that's the geoid. And because we cannot map this, we have to rely on the datum, which again is going to be a mathematical average. So that is this blue line taking the average of where the actual geoid exists. And so you can see how the true center of the geoid would be this square. But when we take into account and create and basically try to artificially smoothen out the surface of Earth, the location, the center of this datum where the XY coordinates can start is going to be slightly off center of the true middle point. So ultimately, the datum is the average location, the quote-unquote true size of the Earth, the true shape of the Earth when we are diving into measuring and using coordinate systems to find accurate locations on Earth's surface. So Earth's surface is going to be this blue line in the world of mapping, which is why it's going to look like a spheroid. But it's important to note that the geoid is the true shape of Earth. As I just said, a datum is an approximation for Earth's shape, and that is used for mapping. But it's also important to note that there are more than one datum, which is why we have datums. And so we can look at local datums, which are going to optimize the shift for a best fit at a particular location. Again, because we can see how this datum might less accurately fit this area of Earth, which is why this is a poor fit. And in other areas around the world, this datum is going to be a good fit because it most closely represents the actual surface of the Earth. A local datum is going to be able to be used to optimize the best fit. And as I mentioned on the previous slide as well, that geocentric or world-centered datum optimizes the fit for the entire world. So that is going to be quote-unquote off-center from the actual center of this geoid. So the center of the datum of the geocentric or world-centered datum is optimized to fit the whole world, while local datums can be more specific as they fit the geoid best. And how many datums do you think there are? Well, there's quite a few. And so most importantly, when we're looking at the North American datum, that's what we would use here locally in North America. You can see that NAD, North American datum, 1927, is basically when this was created or put together in 1927. More recently, and this is more popular, that the one that gets used is the NAD 1983, which is the first choice if you assume an unknown datum set for an undocumented data, again, in North America, because this is the datum that is most accurately fit to what the actual geoid looks locally. And so there are a variety of different datums depending on what scale we're looking at. And so again, the World Geographic the World Geodetic Survey of 1984, WGS 84, this is the one that is looking at the geocentric datum, right? The mathematical middle point of the datum that we are using when we're looking at the whole world. So you will become very familiar with these different datums as we work on the different maps throughout this class. And when you are choosing a datum in the mapping software, you will see them listed as such. And sometimes you'll need to assign a specific datum to your data set. Again, most commonly when we're going to be working with data, it is going to be the NAD 83. But this may choose, probably not for our class, but this may, you may have to choose something different in the future depending on the scope of the work or the scale of the map that you are creating. So we also will have to change or project or transform our data if all of our data is not projected to not only the same coordinate system, but if they're not using the same data. If we are using different datums, then the data that we are attempting to project will not align and your map is going to start looking real funky. And at times it may be necessary to convert from one datum to another. We call that a datum transformation. It's going to require some estimating or guesstimating to get the fit just right of basically how one data set sits on top of another. And because this is not exact and because it's nearly impossible to arrange the data that was collected using different datums, you want to minimize the amount of conversions that need to be done, and it should only be done when absolutely necessary. And so the more often that you convert datum information or that you transform these datums, the less exact your map is going to look. So this is definitely something that you want to minimize as much as possible. If you are going to be tasked with performing a datum transformation, you are going to get a warning that it's going to look like this, but it's just important to note that the data will not be matching up absolutely perfectly. And the same note goes for if you are using GPS coordinate systems or any other data that you've collected where you are attributing the XY coordinate pairs. You have to set the datum as you're recording, and you have to remember what data or what datum you are using so that you can accurately present it on a map in the future. The default datum may not be the one that ultimately you want. If you know that you're working with North American, you want to be working with a North American datum, you definitely don't want to use something that is most accurate on, in Australia, the other side of the planet. So it's really important to note that whenever you're collecting data or whenever you're working with data, looking back to that metadata, right, the data about data, it's important to record everything, knowing exactly what you're doing so that when you are collecting your data, or you can reference back to the data you've collected when you are running into an issue, you should ideally be able to figure out where you went wrong. So now that we have a better idea of what the backbone is of coordinate data, coordinate systems, the datums that get used to arrange this, let's take a closer look at the projections. As we've mentioned previously, a projection, again, is that mathematical conversion of points, taking the continent data or Earth's surface data from that spherical planet and transplanting that onto a two-dimensional piece of paper. And you already know that depending on which projection you're going to use, it is going to affect or shift where surface data is going to exist on your map. So every projection is going to have an underlying geographic coordinate system. And projections based on different datums will be offset from one another. Again, this goes back to when we are collecting data or when we are projecting data. And so you can see in this image that while we are looking at two different data sets, we have the aerial photography and then the line data, you can see how these streets do not match up perfectly with what we're seeing on the map. So in essence, what this is just trying to show you is that these trails or these roads that exist in this photo, right? This loop right here looks like it should be right here. You can see how this street coming down here is probably this street coming down through here. You can see how this data is shifted and it doesn't match up perfectly on the map, and that is due to a difference in not only the projections used, but the datums that were used to create those projections. So again, the slight differences in where that data is collected from or how that data is portrayed is going to result in skewed maps.